Thank you for the invitation to be here today for talking about my last studies. I am postdoc at University of Oviedo in North Spain and also a visiting researcher at the Czech University of Life Science in Prague. So during my PhD, I was working in soil nanoremediation using especially nanoscale zero-valent iron for remediating soils polluted by metalloids. But now I'm trying to apply the combination of this nanomaterial with other organic amendments, such as biochar. So first, I know that people who is attending this webinar has previous knowledge about biochar, but I would like to introduce about soil pollution first. So the soil pollution is when there is presence in the soil of a chemical or substance out of place. Normally, it's presented in higher concentration than the normal one. So according to the geological background, we have some concentration of some elements in the soil. And when we have higher concentrations than this background, we can determine that the soil is polluted. And we have also the other aspect of bad effects on some organisms. So the main pollutants affecting soils in Europe are the ones that are shown in this slide. And regarding the 35% of the pollutants are metalloids. So I would like to center this webinar in these pollutants. So metalloids, also named heavy metals or potential toxic elements, are this group of chemical elements of environmental concern that they are in the environment, they are persistent, so it's not eliminated naturally, and they are biomagnify and bioaccumulate in some organisms. So for remediating soils with these pollutants, we need to decrease the mobility of the metals and the availability. And the availability is the accessibility of these chemicals to be assimilated and to be possible toxicity effects on the organisms and can be defined by different chemical methods. So some other similar concepts are leaching or mobility or availability. So our target is to identify some remediation technologies to reduce the availability of these metals and fix the metals in the soil. So for example, we can find some metals such as copper, lead, and zinc, but we can also find metalloids such as arsenic, antimonium, or selenium. So using the first remediation technology, soil stabilization, try to decrease this pollutants availability using amendments, usually organic amendments, such as compost or biochar. So the application of biochar to the soils for fixing the metals in the soil, it's a stabilization technique. The nanoremediation technology tries to decrease the pollutants availability also, but using nanomaterials. So it means that the size of these amendments are very, very small. So we have high surface area and high reactivity. So the efficiency usually is higher than the microparticles, especially at the short term. And the last technology that I would like to talk is phytoremediation, which is related to the use of plants for immobilize the pollutants in the soils through the mechanism of the roots, or also to extract the pollutants from the soil through the roots and translocate to the other part. So it's possible to extract the pollutants or to immobilize the pollutants. So the idea to combine biochar, nanoiron with plants is to immobilize the pollutants in the soil, avoiding the translocation of the pollutants from the soil to the plants. So the application of the biochar for soil stabilization is not only focused on the immobilization of the pollutants. We have different effects. The first one is the most important for us is the immobilization of lead, zinc, cadmium, copper by different mechanisms. For example, electrostatic interaction or ion exchange, complexation, or precipitation. But we have also other good inputs For example, we can improve the soil physical chemical properties, we can improve and increase the water holding capacity, add nutrients to the soil, improve the pH in case of acidic soils. So we have a versatile material that can resolve not only problems about pollution, but also from the point of view of restoration or degraded soils. And then, on the other hand, we have the nanomaterials. For example, for nano-iron, nanoscale zero-valent iron, it's very good performance for immobilizing arsenic, for example, and other metals, but just only for immobilizing. We are not adding nutrients to the soil, improving other parameters of the soil. So from this point of view, the biochar, it has more advantage than the nano iron. However, we are comparing these two materials. We can identify higher rates of the immobilization for the nano iron. But our idea to combine the nano iron with the biochar in a composite or mixing both amendments is because of the presence simultaneously of metals and arsenic metalloids. Because we identify that the application of biochar it's very useful for immobilizing the metals, but in some cases can mobilize arsenic. So there are works in the literature reporting that the application of the biochar can increase the dissolved organic carbon so our idea was to mix both because we have the nano iron that it's excellent for immobilizing arsenic with the biochar, so we can solve the problem of arsenic. So how can we modify the biochar using the zero-valent iron nanoparticles? The first mechanism is the metal impregnation, using different metal oxides during the synthesis of the composite or by mixing directly. But we have a lot of effects of the modification using other methods. We can use ball milling for physical modification, modify the surface of the biochar with chemical modification in acidic or alkaline. We can use other like graphene oxide, application of biofilms, bentonite, but our idea was using the metal impregnation. So we tried two different ways. The first one was mixing directly the nano iron water suspension with the biochar that was produced at different temperatures in a pyrolysis furnace, and then mixing with the soil. So we are mixing all together, and we have some advantage and disadvantage. The first disadvantage was that the nano iron is very reactive. So when we are adding to the soil, for mixing the soil with the nano iron, we have some problems because of the aggregates of the soil particles. So them mixing with the biochar particles is quite difficult. And then we have the impregnation to create nanocomposites. So for the nanocomposite synthesis, we were using sawdust as a precursor, mixed with hematite with the nanoscale. In water, we mix this mixture for a time, then we dry at room temperature, and then we pyrolyze the mixture at 700 degrees for 4 hours in a nitrogen atmosphere. So we are generating a nanocomposite in which we have the biochar particles with the nano iron inside the pores of the carbonaceous material. So usually we are working at different scales. We have some experiments using incubation in tubes, using just only the contact of soil and the amendments in tubes with different water holding capacity, different rates of humidity for monitoring the pollutants availability. Then we have pots with plants in order to monitor if the plants are uptaking the pollutants from the soil or not. Rice boxes in order to analyze the roots, but I will come back later with this type of experiment, and then also some experiments at pilot scale. So we are working with several soils from real brownfields that are polluted areas, but especially located in North Spain, in Asturias, which is my region. So the first region that I will introduce is Langreo, which is an urban decline area. It's not so big. It's a coal and steel region in transition because now this mining and industrial activities are closing. So we have a lot of areas very polluted by different pollutants. So we have this Nittestur site, which is a former fertilizer plant that was abandoned in 1997. So we have a pollution mainly by arsenic and lead. So we have a metal and a metalloid. We have affection to the soils and the groundwater. And we have 20 hectares of the site, so it's quite big. So the cost of the remediation it's very high. So we have a black field because there are no soil demand, and the current landowners are not responsible for pollution, so they don't want to know about their remediation costs. So according to the historical evolution, we were able to determine which was the cause of the pollution here, and we found the presence of buried ashes, a lot of tons of this residue that was generated by the roasting process that the industry was performed in order to create the sulfuric acid. And this material is mainly iron oxides enriched in arsenic, lead, and zinc, and other metals. And now the water table, it's washing this material because it's changing a long time. So when the water level is increased, it's in contact with the Paris ashes, and we have some sulfurs that were not totally roast, and we have acidic leaching. So we identify some parts of the site that could be very nice for trying our approaches. And we perform both experiments using the buried ashes directly mixed with compost, biochar, and nanoiron. And we test the soil with a plant, with the Brassica juncia. And then we went to the pilot scale experiment in order to control conditions, but in a big amount of soil, because the amount of soil in the pots was 1 kilo. And the combination of nanoiron and biochar here was by mixing. So first we add the nanoiron, and then we add the biochar. So it was sorry, it was the opposite. First we add the biochar, and then we add the nanoiron, because the biochar particles were increasing the volume of the soil, and it was favoring for mixing the nanoiron later. And as you can see, the nanoiron decreased the amount of plants that were growing in our plots. But the combination with nanoiron and biochar, it was intermediate value between nanoiron and just only biochar. So for well, we monitor also the microbiology aspects of the soil and some parameters related to the plant physiology. But for us, the most interesting was the polluted concentration in the real part, because we found that the copper concentration was lower, is in the yellow color, is lower in the case of the biochar and nanoiron plus biochar. So the biochar mechanisms for immobilizing copper was better than the nanoiron, and it occurs the same for the zinc. But then, for example, in the case of lead, we found that it was a synergy between both amendments, because we obtained better results in combination of nanoiron plus biochar than the application of both separately. But the most interesting part is the arsenic, because we were able to immobilize the metals using the biochar, but we were immobilizing the arsenic. So for us, it was very interesting that the combination of both amendments, the biochar plus the nanoiron, decrease metals mobility, and also decrease the arsenic leaching that produce the biochar. So we are not remediating the arsenic availability, but we don't have worse behavior of this element. And then we have some products like proline, that is one indicator of the plant physiology, that reveal that the biochar in both cases, alone and in combination with nanoscale zero-valent iron, increase this value. So it means that the plant is fighting against the presence of pollutants inside. Then regarding the impacts on soil microbiology, we were very worried about that because sometimes we detected a bad impact, a negative impact on soil microbiology because of nanoiron. So we were thinking that the combination of nanoiron and biochar can be good for that. And we found that in that case, there are not very big changes, just only in the combination of both of nanoiron and biochar, we determined that there are at the last monitoring time that there are some differences, but are not very big. But looking for the abundance of the microorganisms, we found that there are higher diversity and higher abundance. So for us, it's not a negative impact, it's a positive impact. And now I will move to other area located in the same region. It's the industrial areas of Apiles city. So now we are in a coastal area, so we have different weather conditions, and we collect soil in the area that it was previously studied in different works that we were dealing with the pollution source in this area. So we identified that the main pollution source in the area was a single smelter. So we identified the sites with the higher influence of the single smelter and collects this heavy polluted soil in order to test the feasibility of the nanocomposite. So for this experiment, it was a experiment using resin box experiment at the laboratory scale, and we used the nanocomposite generated as the previous was indicated. So using these rice boxes, we have different box with a soil compartment. We have the polluted soil with the sandy soil, and then we have sand as a control for the leaching of the pollutants from the soil to the potential groundwater in the reality. So we have rhizomes in the other part of the rhizome boxes to take the pore water. So we were able to take the water in the soil because the soil was saturated at 70% of the water holding capacity through these fibers, black fibers here. So it was possible to collect the pore water at the end of the experiment. And then we have some boxes with plus nanoiron. That's why this the color of the soil is completely different. Oh, sorry, it's dark because of the nanoiron, and also with the composite of nanoiron and biochar. So after 45 days, we were able to grow plants. It was Agrostis capillaris, which is a grass outside the soil, because we could put this membrane close to the soil, and we have the plant compartment separately to this soil compartment. So after the germination of the plants, the roots were growing through the, not through the membrane, close to the membrane, in order to take the water from the soil, but without being in contact with the soil. We did this experiment because we were interested on looking for the roots in order to know if the nanoiron coming from the soil it's stick on the roots or not. And our idea was to evaluate if we have negative impacts coming from the nanoiron, because we have small particles. We were worried about if the plants are able to uptake the nanoiron because of the small size of the particles. And we want to compare if the nanoiron, when it's inside the biochar, it's there and it's not released and available for the roots, but it's still efficiency for immobilizing the pollutants. So we monitor the pore water by determining this metal concentration in it, and we determined that the cadmium, lead, and zinc concentration in pore water in the controlled soil, the soil without amendments, was very, very high. But after the application of 2% on weight of the nanocomposite and the nanoiron, the concentration was extremely decreased. And then comparing also these concentrations that are from the pore water taken in the sand, the clean sand, it was possible to observe a leaching process from the soil that could be affect to the potential groundwater in the real site close to the sea, but it was decreased after the application of the amendments. And then regarding the fresh biomass, we observed that the application of the nanocomposite increased the fresh biomass obtained from the aerial part and also from the roots. So the plants were growing under better conditions after the application of the nanocomposite instead of nanoiron. That it's consistent for us because we are adding nutrients to the soil. And then we have also the concentrations of the pollutants in the aerial part. And it was possible to observe that the application of the nanoiron, which is orange color, and the nanocomposite, its gray color, decrease the concentration in the aerial part, not only in the aerial part, but also in the roots. So for us, it was very interesting to see that it was quite similar for arsenic and cadmium copper lead, but it was a bit worse for the nanocomposite for zinc. But we have higher quantity of fresh biomass, so we need to have a balance, which is better in that case. And we were worried about the iron. So we observed the iron increase in the other part, which could be related to the uptake of the nanoiron, but it was a bit decreased in case of the nanocomposite. So it looks like the nanocomposite retained the nanoiron in the pores of the carbonaceous material. So it's decreasing this negative effect. And then we have some photos, some pictures at some of the roots. And we have the current roots of the plants growing in the soil, in the control, or outside the soil. And then we have this brightness colors around the roots in the nanoiron treatment, which means that the nanoiron comes through the membrane. It was attached in the roots. But in the case of the nanocomposite, we also detect this nanoiron, but in less amount than in case of nanoiron. So it is in accordance with the elemental concentration analysis. And finally, to finish the presentation, I want to show some perspectives that we have now in our head. And we are testing the compost, biochar, and nanoiron mixture. So for us, the combined application of compost and biochar can be better than the only application of biochar, because the compost is releasing nutrients very fast, but biochar is releasing nutrients a long time. So in the short term, we have the compost and the nanoiron for giving nutrients to the soil and immobilizing faster the pollutants. But then we have the biochar for the long-term experience. So until now, we have just only some results coming from the short term, and we have differences between the untreated soil with the treated soil. So we have a lot of grass in some plots treated with compost and biochar, but not in the others. So it's a good signal by the moment, but we need to wait some years in order to evaluate the long term. And then for some time to time, we were removing the grass and putting different trees in order to evaluate in a second step what's coming with different plants, in order to evaluate just not only grass, but also big plants. And I would like, before finishing, to thank to the team. We are located in North Spain. We are different people coming from different background. I'm mining engineer. We have not only engineers, we have biologists, chemistry, experts on geology, geography. So we have a complex institute with different profiles that for us it's very good because we can combine different approaches for the same problem. And well, also to say some of our collaborators, especially in the Czech Republic, the Czech University of Life Science in Prague and the Czech Advanced Technology Research Institute, that they are experts on the synthesis of nanoiron and the nanocomposite. Also people coming from the University of Orleans, Warsaw, and then some people coming on from not for abroad, but also from Spain, in Midra, Irme, and in Carthagena. So thank you for your attention. Now you have some questions, I can answer you. can also check my email, and you have my profile in ResearchGate or Instagram, where I'm trying to post some pictures of the different experiments that we are performing, and also in LinkedIn. So thank you for your attention.
Thank you very much, Diego. That was quite some work that you already did there, or you and your team. Really impressive. So the question and answer session is open. So if you want to ask a question directly, just unmute yourself or write it into the chat. And usually that takes some time. So my question would be, so did you check for leaching of nano iron from the soil? So is that happening?
Sorry?
Is the nano iron also leaching from the soil, or is it staying there? Did you?
Yeah. Nano iron, after the application to the soil, start to aggregate and oxidize. So nano iron, it's a core of zero-valent iron, but then we have some iron oxides around that are because of the oxidation. So when we are applying to the soil, nano iron is starting to oxidize. So the iron oxide increase the size of the particles. Then by reactivity, they aggregate, they attach to the soil, and they are not nano. So we have just only a few nanoparticles in the soil. There remains as nano, because we have microparticles because of the aggregation. So that's good, because we have not leaching because of that. But these particles that are not faster than the others start leaching because of the water. So under our experience, we are applying the nano iron under good climatic conditions when it's good weather because of that.
Okay. I saw for a second the hand was up. Maybe it will come up again. Any questions so far from the audience? Otherwise, I will just continue. Because I had a second question. So about the remediation of contaminated soil, what is the threshold after you say it is done, or what's the threshold for success in that case?
Yeah, well, the most useful technology is to dig the soil and transport to a landfill, and we are removing the pollutant. But in order to decrease the cost of the remediation, we try to immobilize the pollutants using nature-based amendments or nature-based solution. They are very cheap, and we are fixing the soil there. The problem is that according to the legislation, we need to remove the total concentration, not the availability of the metals. So, for example, in our region, well, in Spain, each region, it's the government of each region is the one who is dealing with the legislation about polluted soils. Because of the geology in Spain, it's very different. So the background concentration, it's different in different sites. So for example, in Asturias or region, we have a legislation that we have some limits that we cannot be above. So we have, for example, for arsenic, we have the limit in 40 milligrams per kilo. If we have higher concentration, we have potential polluted soil. So we need to determine a risk analysis in order to know if we have risk for potential receptors. So we need to identify if there is risk or not. And if there is risk, we can justify that we can immobilize the pollutant in order to decrease the migration of the pollutants to affect to a potential receptor. So for that, we need to perform several documents, and usually we are working with companies in order to tell to the administration that it's possible to reduce the availability. But then the government needs to approve, and we are fighting with them in order to justify that it's possible to reduce the risk. So by the moment in Nitrostur, we were able to do it, and now the government approved the application of compost and other amendments to immobilize the pollutants. But it was very difficult to deal with these government, because according to the legislation, you need to decrease the concentration. That in most of cases, it's almost impossible.
Basically,
so this is the big deal.
Digging it out is the standard practice.
Yeah.
Okay, great. Thank you very much, Diego. You got a question from Ingrid. Do you think you will need to reapply nano iron or iron after some time?
That's a very good question. We have one plot that we treated with a nano iron in 2016, 6 years ago, and we were monitoring for these 6 years, and the arsenic and mercury concentration was decreased after 3 days, and it remains the same along the 6 years. So by the moment, it was not necessary to apply more nano iron. In one plot, there was very extremely high arsenic concentration. It was like 40,000 milligrams per kilo. That's very huge amount of arsenic. We apply nano iron after 8 months, but now it's totally immobilized. So by the moment, it looks promising.
That sounds good. And I guess that's a really important part of soil remediation, that it's for longer than a couple of months. Thank you very much, Diego.